a little grab bag. Oh, not red. AP test grab bag. So a few more topics, little bits of things to remember, or stuff we just didn't have time for. So again, on the AP test, you will be able to use any notes or calculators that you have access to. I highly recommend Desmos. You have to download it on your phone or get another computer to use, because the one you're using for the test will be locked. Make sure you have either access to your phone or another computer to use Desmos and any other calculators that you want. All of the work on the AP test will be on the computer. There will be no phones to upload or anything else pictures to upload or anything else like that. It's all typed in the computer. So getting some practice with Desmos, typing things in, that'll be useful. And I'll go over what's on it in a little bit. But let's go to this grab bag. The first thing I want to talk about in this grab bag is a rule called L'Hopital's rule. L'Hopital's rule. Whoopsies. Also called the hospital's rule. Sometimes they put an S there. L'Hopital's rule. This has to do with limits, for limits. Little thing, very useful rule. L'Hopital was a French mathematician back in the 1800s and sort of figured out this rule here. So basically it's used when you have a limit, when a limit equals 0 over 0 or infinity over infinity, you can use this rule. The limit as x approaches whatever value c of f of x over g of x so you have some limit of two functions dividing each other. And when this limit equals 0 over 0 or infinity over infinity, and you get a situation where you have like a basically indeterminate form. Indeterminate. What you do is take a derivative of the limits. Take the derivative of f and g and do the limit again. So basically, the limit as x approaches c of f of x over g of x, instead you change it to the limit as x approaches c of f prime of x over g prime of x. So L'Hopital's rule, or L'Hospital's rule, you do the derivative of each section, f and g, the top and the bottom, not using the quotient rule, just each separately, separate derivatives. You do the derivative of the top and you do the derivative of the bottom, and you do the limit again, and you get the answer, and that'll be the same thing. It'll equal this answer here. So this is only true for limits when you have a 0 over 0 or infinity over infinity. So let me give you an example. An example here would be, let me see, something like, I have my examples here. So we have like the limit as x approaches 0 of x over tangent x. So if I ask you to find this limit, for example. Bianca Perriso, welcome. Maria, welcome. This is a little what we're doing today is a little grab bag of information for the AP test. Stuff we didn't have time for during the regular year. We're just going to grab bag some stuff today, and I'm going to talk about how we're going to end this semester. So, first rule, L'Hopital's rule, is a solving for solving limits when you have infinity over infinity, so or 0 over 0. So for example, in this limit here, to try to solve this limit, if you plug in, you're going to get 0 over the tangent of 0, which is 0 over 0. So we have to fix it. Find the derivative of each of the top and bottom parts, right? So we're going to find the derivative, d dx of the top and d dx of the bottom. Use L'Hopital's rule. You do the derivative of the top and the derivative of the bottom. So this becomes the limit as x approaches 0 of, well, now derivative of x is 1. The derivative of tangent, oh, who remembers what that was? Derivative of tangent. What was that derivative? Somebody remembers that, hopefully. All these trig derivatives, close, very so. Secant, the derivative of secant is secant tangent. The derivative of tangent is connected to secant. Secant and tangent go together, but the derivative of tangent is instead secant squared. Yep. Very good, Stephanie. Jessica, welcome. The derivative of secant is secant tangent. The derivative of cosecant is cosecant cotangent. But the derivative of tangent and cotangent are the secant and cosecant squareds. So, now let's try the limit again. You do the derivative of the top, the derivative of the bottom, and you do the limit again. Limit of x approaches 0 of 1 over secant squared. Well, that's going to be 1 over the secant squared of 0. Welcome back, Jessica. And the secant of 0, what's the secant of 0, everyone? Well, I don't know what the secant of 0 is, but I know that secant is 1 over the cosine of 0. And cosine of 0 is what, everybody? Cosine of 0 is how much? Look at our unit circle. Let's think about our unit circle. Cosine of 0. Unit circle, 0 is here. Cosine is flat. Cosine of 0 is 1. 1 over 1 over 1, which is 1. So this limit, as x approaches 0, of x over tangent x is equal to 1. Because you find the derivative of the top, the derivative of the bottom, and you figure those out. Is that okay, everyone? Everyone got that sort of process here? So one little quick rule, L'Hopital's rule. Small rule, but something to remember. Whenever you have a derivative, whenever you have a limit, I should say, whenever you have a limit approaching 0. So, Jessica, what we're doing is just a little grab bag of material at the end here. A couple of things I want to mention that we just didn't have time for. And one of those is something called L'Hopital's rule, where if you have a derivative that equals 0 over 0 or infinity over infinity, then you take the derivative of the top and the derivative of the bottom, and you find the limit again. And you can do this as many times as you want. This works in like a chain. You can keep going. So if you do the derivative the first time and you still get 0 over 0, do it again. Do it again. All right, you want another example? Maybe what about something like, what's a good one here? What about this one here? Another example. The limit as x approaches 1 of, let's do x squared minus 1 over, let's go, the cosine of x. Sorry, no, not cosine. What am I doing? Not cosine. Over, let's do, let's see, I'm trying to make a 0 here. Let's do That's a good one. Over x minus 1. That's just... No. That's too boring. Hold on, everyone. Let me think. Let's do the sine of... Nope. Yeah, sine of 1 minus x minus 1. Why not? Something like that. Sure. Ooh, no. You know what? I have a better idea. ln of x. Haha. Yes. Perfect. All right, let's try this one. The limit as x approaches 1 of x squared minus 1 over ln of x. Well, if we plug in 1 squared minus 1 over ln of 1, 1 squared is 1, 1 minus 1 is 0. ln of 1, if you plug that into a calculator, you're going to get 0. So we know that we get a 0 over 0 for this problem if we plug it in. So we can use L'Hopital's rule and find the derivative of the top and the derivative of the bottom. And so I can find the limit, oopsies, the limit as x approaches 1 of, well, what's my top equation now? This becomes 2x over, the derivative of ln was 1 over x. So now if I plug it in, I'm going to get 2 times 1 over 1, which is going to be 2. So you can see you can use L'Hopital's rule for any kind of situation here, where you have a limit that equals 0 over 0 to start, find the derivatives, and then you get your answer much easier that way. So let me show you, if we do this limit here, I can visualize this with a graph. And again, I want to show you that a very useful way to do this problem, these kind of problems, even with limits, is with Desmos. If I have this limit equation and I want to try to solve it, let's say I didn't want to go through all this process of finding derivatives. If I plug this equation, into my Desmos, let's go to Desmos, x squared minus 1 over ln of x, x squared minus 1 over ln of x, right? And I'm approaching x equals 1, right? X equals 1. Here you see, oh, you can't quite see that they don't touch, but you see they meet at 2. So it doesn't give you the intersection because it's undefined, but the limit, you can see the limit approaches value of 2 here. So you can use this visually as a guide as well. As a guide as well. Kind of funky looking equation, everyone, right? Look at that, weird equation. But there's your limit, right? So you can use this graphing as well. Another way you can use Desmos is to graph for limits. Plug the equation in. See if you can find that limit. All right. So that's one little grab bag, is L'Hopital's rule. Let me show you the next one. Another quick little grab bag is particle motion. Particle motion. So I guarantee you there will be at least one question on the AP test that involves motion of a particle on a line, right? So we've talked about this a little bit, but just to be explicit about it, a few things to remember. And in your reviews, where's my review here? In one of the reviews that we did on Friday, yesterday I should say, in the AP test review section, section number 6 here, particle motion, differential equations, and the rest. This is a good explanation of the kind of topics of particle motion that we need to remember for the AP test. And they have some good sort of notes here about particle motion and the different definitions. This one here about speeding up and slowing down, right? But this terminology is probably the most useful thing. So with particle motion, it involves three equations. There's x of t, which is the position equation, position function. This is the where. V of t, which is the velocity function, velocity, which is how fast, right, your speed. And then there's the acceleration equation, acceleration function, acceleration, which is speeding up or slowing down. Speed up or slow down. And the things to remember about these equations is their relationships. If you take the x function and you do the derivative, that is the velocity equation. The derivative of the position function gives you velocity. And similarly, if you have the velocity equation and you do the integral of it, that gets you the position. Right? The integral here, this integral is a measurement of change in position. Measures the change in position. How your position has increased or decreased. If you integrate the velocity function, you have information about whether the particle has moved to the left or to the right. How much the position has changed of your particle. And the same happens with acceleration and velocity. If you do the velocity function and you do the derivative of velocity, you get the acceleration equation. And similarly, you integrate the acceleration equation, you get the velocity function. And again, this integral of acceleration measures the change in speed or velocity. If you integrate the acceleration equation, it tells you how much the speed has changed. They love to give you questions about velocity, acceleration, positions of particles, give you one piece of information, ask for another. So if they give you the velocity equation and they want to know the position, know that if they give you the velocity function and they want the position, you're going to have to do an integral, right? But if they give you, let's say, the position function and they want to know the speed, you're going to have to do a derivative. Or similarly, if they give you position, the velocity, and they want the acceleration, you have to do a derivative. So know which direction you're needing to go. If they give you one of these and they want a different one, remember if you're doing a derivative or an integral. Which direction are you going? Okay? Make sure you know those directions. And the other thing is about graphs of these functions, right? So if they give you, let's say they give you the x graph, right? Various important features of this graph. At here, here, and here, x prime, which is the velocity, equals 0. At these locations here, here, and here. So given the position function, you can see where the velocity is 0. right? So those are those graphs there. You can imagine the velocity function, right? It's going to be positive here. V is positive here, and velocity is negative here. You're imagining all the tangent lines. Velocity equals tangent lines. So you have a positive velocity, you have 0 here, negative 0, positive 0, negative. Right, so you see you have your 0 velocities here, positive, negative velocities there. If they give you the velocity functions, say they give you the velocity equation. Let's do it a different look. Let's go like this. For the velocity function, you can see here, and let me do this better. Let's go like this. For the velocity function, there's a few key pieces here. Here, the particle is stopped. Right? It is no longer moving. It is 0 velocity there and here. I guess and here, right? Particle is stopped at these 0 locations here. When the velocity is positive means it is moving to the right. Moves right. And when the velocity is negative, it moves to the left. This direction is faster as you go up that way. And when you go further down, you are also going faster. In the middle here is when you are slow. Slow, near 0. Right? The velocity function tells you the speed. If you have a high positive velocity, you're moving very quickly to the right. If you have a high negative velocity, you're moving very quickly to the left. When you are close to 0 is when you are slowing down. High velocity, low velocity. The further you are from the x-axis, the faster you're moving. For the x position, the further you are is the distance. This is further distance. Further in the x-axis is further away from the edge, from the center here. Particle speed is 0 on these locations here. That's like these locations here. Particle speed is 0. It's not moving. That changes direction. Now it's going down, right? Now it's going negative velocity. It's moving to the left now, right? It's going quickly, speeding up, slowing down, stops, then changes direction, goes backwards, then slows down, stops, changes direction, goes forwards, right? Slows down, stops. So the things to remember with the particle anyway is about your acceleration. If your function, let's see, what color am I going to do this in here? I want to do yellow, but maybe green? I don't know. For acceleration, oh goodness gracious, acceleration the increasing speed and decreasing speed. You're looking for increasing speed and decreasing speed. Look for increasing speed and decreasing speed. So if you are, for example, positive and going up, you are acceleration is positive. If your graph is going up, right, the derivative is positive, and the function and the speed is increasing, right, you're going up. Here, the acceleration equals 0. Positive here, 0 here. Here, the acceleration is negative. So you see how you're going away from the line, your acceleration is increasing. Acceleration is positive. You're increasing, right? You're going faster. Here you're going slower. Here you are not changing, your acceleration is flat. Your acceleration is constant. Your velocity is constant. So you have a constant speed when your acceleration is 0. You're increasing your speed if your acceleration is positive and velocity is positive. You're decreasing your speed when your velocity is going closer towards 0, right? And the same thing happens down below. Here, let me do it here. Here, your acceleration is negative, but you're going faster. Here your acceleration is 0, and here your acceleration is positive, but you're going slower because you're going towards 0, right? Towards 0 equals slower, slowing down. Away from 0, away from 0 equals speeding up. So just a couple of things to remind yourself about for the acceleration and velocity functions. Again, a little grab bag of information, things we didn't quite have time for. But I guarantee you there will be questions about velocity functions and particle motion on the AP test. What other things can I share with you? So one more thing. I think we have time for one more. The last one is a few special derivatives. Special derivatives. These are not likely to be. You're not likely to see these derivatives. You're not likely to have to find these derivatives. However, there may be one or two multiple choice questions where, if you know these rules, you can find the answer. So one of those is the derivative of log base b of x. The derivative of a logarithmic function, not ln, right? We know the derivative of ln, d dx of ln of x is 1 over x, right? This is a derivative of a log base anything. ln is log base e of x, right? So log base e is ln. Well, what if it's like base 2 or base 10 or base 5 or whatever, some other logarithm, right? What's the derivative of that? Well, this is ln b times 1 over x. Let me just verify. Ln b of 1 over. Oopsies! Stop it! So you see these little derivative rules. Make sure I'm saying the right thing. Again, this is not something that gets used very commonly, but okay, not quite correct. Not quite correct. Sorry, everyone. Hold on. It's 1 over x ln b. ln b is on the bottom. I knew there was an ln b, I just didn't know where it was. So if you need to do the derivative of a log-based b function, it's 1 over x ln b. Another special derivative is for an exponential, a to the power of x. The derivative of a to the power of x and that again involves ln, right? So we know the derivative of, for example, we know the derivative of e to the x is simply e to the x, right? For a to the x, it's a to the x ln a. That's the derivative of a to the x. So if you're using something that's not e or ln, a regular log or an a to the power of x, it involves the natural log. Involves the natural log like this. And all of these rules, by the way, in your important handouts section, I give you these useful formulas, calculus, derivatives, derivative rules, all these important handouts here. They have all these rules for the derivatives, limits, right? Here's L'Hopital's rule. Here's L'Hopital's rule. But here's, for example, a to the x is a to the x ln a, or log base x is, a log base a is 1 over ln x ln a. And then there's also all these derivatives for the inverse sine, cosine, and tangent, which are useful to be able to recognize. So let me quickly give you a couple of those just to remind you, so you have them on hand. Inverse sine, or arc sine. They use both these interchangeably. Sometimes they put the inverse, sometimes they put arc, right? Inverse trig derivatives is 1 over radical 1 minus x squared. Let me just make sure. 1 over 1 minus x squared. Yeah, there's inverse sine. So when you see this, if you have, for example, 1 over 1 minus x squared, some kind of complicated looking square root with a crazy looking radical on the bottom, recognize this as the inverse sine. It's a positive, right? Positive 1 over radical 1 minus x squared. Inverse cosine is almost exactly the same, or arc cosine. Arc cosine. It's negative 1 over radical 1 minus x squared. So cosine, as always, cosine is negative. The only difference between sine and cosine is one is positive, one is negative. The last one that you're likely to see is the inverse tangent, or the arctangent. That one is 1 over x squared plus 1. Here's inverse tangent. 1 over 1 plus x squared plus 1, same thing. So these three inverse trig derivatives, this is the connection here. Cosine and negative 1 over x, 1 over 1 minus x squared of 1 minus x squared. Sine is positive 1 over 1 minus x squared. And the tangent is, goodness gracious, the tangent is 1 over 1 plus x squared, or 1 plus x squared. So these are some things to write. Again, there may be one question on the AP test or two questions in the multiple choice section that says, what's the integral of this? Or what's the derivative of inverse cosine? Which of the answers is it? And so if you can recognize these answers, that'll be useful for you. Okay. So just a few bag things I wanted to mention today. Oh look, we reached the end of the thing. Almost like I planned it that way. Some special derivatives, some particle motion situations about acceleration, velocity functions. Really just stare at this for a while and try to understand what's happening here with its position and velocity equations and the connection between these three functions, the connection between these functions. And L'Hopital's rule, make sure you remember L'Hopital's rule on limits, where you take the derivative of the top and the bottom and you find the equation that way. If it equals 0 over 0 or infinity over infinity, do the derivative and then solve your limits that way. All three of these are probably going to be a couple questions. I know the particle motion is going to be, there's definitely going to be one free response question involving particle motion. And there may be a couple questions on these special derivatives. Just be able to recognize them for the log and a to the x exponential equations, and then your inverse trig if they come up. Just keep these in your hat. Keep these in your hat. Make sure you can figure out how to use them, know how to use them on the AP test.